we stopped exactly in this part, I think. Yes, we were here. So this is an important part in the overall CLIP paper. So you take a batch of N, which is image and caption pairs, and you run the N images through the image encoder and the N captions through the text encoder. So after you do the projection and normalization, then you have the N that you had by 512. So you have this image matrix, and you have a text matrix of the same dimensions. So then you do the multiply the image and the text, and then you get the N by N similarity matrix. So when you look at the similarity matrix, what you would have wanted here, you would have wanted the diagonal would be with as a high value as possible, because the image and its relevant caption, of course, you want it to say, yes, it's the same. Versus other things which are not, so anything outside of the diagonal, so these are not. Okay, so this is a part, so this is for this part. So overall, what the loss tries to do, so like I said, the diagonal entry should be high, the off diagonal should be low. We have here, of course, column, okay, and the final loss, which is the average of the two cross entropies. Okay. Now, overall, just remember when you look at it, right? Remember that it's the different text captions where one of them is relevant to what you have in the image. Now here, I think, the aspect of the data or cleansing of the data, especially when you're generating these metrics, is critical, because if I just fetch images from the internet, then I am going to get images where I have two classes, right? Because maybe I have image of a cat, but hey, this cat is in the street and there are also cars over there. So then for that image with some captions that speaks about cars, probably it's also going to have some high score, okay? So I think this is also very critical there. Okay, so the model there of the paper is trained against this objective. So let's have a look. So we have the image encoder, could be some backbone of a ResNet or some vision transformer. We have some text encoder for it. We have the mini batches. So we have the mini batches for the images, mini batches for the text. We have the projection that we learned. So going from the images to the embeddings and from the text to the embeddings. And we have a learned temperature here, learned temperature parameter. So the first thing we do, we run the images through the image encoder. So we have this part. Then we do the multimodal embedding. So we have here the dot product of the images and the learned projection. And here we do the same for the aspect of the text with its learned projection. Okay, so now we have the embedding, the encoded part. Then we are doing pairwise cosine similarity. So it's this part, and then we have this exponent. So then the result here is the logits. Now this is the loss part. And you remember that the diagonal is representing what should be the correct answers. So given that we have here the labels, we have the coarse entropy loss of the logits that we had here. And here similar. Okay, so this is the computation that we have for the loss overall. So if I summarize everything, so the first 7 lines, they are the inputs and the learnable parameters, the 2 encoders, the 2 projection matrices, the WI and WT that map from each encoder native dimension to the joint D underscore E, which over there for the vision transformer it's 512. Lines 9 till 11. They are running the batch of the images through the image encoder and the same batch through the text encoder. And we have the raw features. And then we had here, following that, what we had here was the joint space, the L2 normalize, and the unit vectors. Okay. So now for the aspect of the zero-shot inference. And this was something very interesting that came out of all of that work. So the procedure for the zero-shot classification, you have there the 4 steps. The first one, you are defining the label set. So what it means, you're defining your classes, and CLIP doesn't care what they are. It could be the ImageNet 1000, or some statement of this is a car, or this is a regular cat, or whatever. And the model was never told about these classes. So step 2, you just take each label, you put it in a prompt. And this part I think we've seen before, where if we had some label of a cat, so we just said the captions that this is a photo of a cat. So you just concat the label that way. Now the reason that we do it that way is that the CLIP's training data was web captions. They look like sentences and they don't look like labels. So the sentence hit the text encoder distribution and just the noun wouldn't. Okay, step number 3. So in step number 3, we are embedding all of the prompts once through the text encoder. So if we do batches loops, we don't need to encode it, right? We encode it once to save this work. So we encode, we normalize, and we store this result according to the number of classes. So that means that for each one of the classes, each one of the labels, we generated this sentence. This sentence we did for it the embedding, and we store it instead of recomputing it. And that matrix is the classifier. So this is the softmax weights. It is learned without ever seeing the labeled training images. Okay, so think about it. It shouldn't, or it doesn't look at the raw images again. It looks at those embeddings that we have. So then for the embedding part, so for any new image that we have, we do encode, we normalize, we matmul with the prompt metrics, and then we do the argmax. So we are selecting the maximal one, and that's the predicted class. Okay, any questions here? Now, a feature that you gain here is that you could change the label set and you don't need to retrain anything there. You can add class, remove class, and all you do is to re-embed the prompts. So this single property is why Clip became the visual front end of half of the Gen AI. Okay, and that's critical there. And by the way, it's very important to grasp this, to really grasp this, because many times I think people that don't know this and don't really know how it works, when they look at classical CNNs, things like this, and they're used to having to annotate some bounding box of some object. If you now need some new class, you needed to redo work. You need to go and annotate the bounding box. You need to train a model with whichever loss function, etc. And here it works differently. You have the images, you have the relevant labels, you're generating these descriptions, captions. It goes through the encoders. So for now, you didn't need to retrain a model. So this is a very strong statement. Okay. So the prompts matter, and this is what we said that impacts the aspect of the accuracy. So for each one of them, you understand, right? So cat, we say, okay, it's a photo of a cat. Okay, so satellite, okay. Actually, I'm not sure about this example. If someone had such strange labeling for satellite, which should have represented not the actual satellite, but this is a satellite acquired image, probably this one, I would edit this. Okay, because same thing, if someone just could give me an image of a satellite, I would say a satellite. But here I see they're referring to a satellite photo of a street. Anyway, so you need to provide it with the relevant context here. You have the ensemble here across many templates. There is the average of the result before normalizing. Okay, so overall, by the fact that we switched from the bare class names to a single template or photo of some class and assembled it across 80 prompt variant, the OpenAI team, they got additional 5% in the points on ImageNet. So it took it from approximately 64 towards this 68.4. Okay, so why does this matter? There are two reasons. So the distribution match, so overall the clip training data, like we said earlier already, it was web captions. So the web captions look like statements of a young brown tabby cat sitting on the, in front of the door. So it just doesn't look like saying, hey, cat, right? So you want to match the data on which the clip model was trained. So that's what the text encoder of it learned to produce. So it produces the very good embeddings, but the structure need to be similar. It's a sentence shape, not just some label. Second thing is disambiguity. So labels could be ambiguous. So for example, crane can be a bird, and it can also be the construction equipment, okay? ImageNet wants the bird, but if you add a context to it, saying photo of a crane, a kind of bird, so this is how you fix this kind of ambiguity. So it also helps you with the domain transfer. So like we said, for satellite imagery, that OpenAI used to say this is a satellite photo of some class. And if it was OCR, they would say this is a photo of the letter A. This is a photo of the letter D. Okay. And there is also the ensemble trick. So instead of one prompt, you could use 80. You could say this is a photo of some class, and you could say this is a blurry photo of some class. Or it's a photo of one class, etc. So this is, we can also say, this is kind of augmentation, right? We have some image or whatever we have, and the caption for it, we could generate many captions that mean the same thing. Now, if you do that, let's say you generated like 80 embeddings, then you average this 80 and you normalize. And then you have something which is more robust. You have like the concept anchor for each of the classes. So the cost for that is this one-time factor of 80 increase in the text encoder itself. And this part, of course, it runs at startup. Okay, so if I summarize this part, so let's say you took the label, you created the different 80 variations of it. For all of them, you did the embedding, then you took the average of this embedding, and now you have some anchor representing the equivalent of the label, but now you are in the Latin space for the embedding of the text. Okay. So this was like a hint of what afterwards became like prompting is a real engineering discipline for LLMs. Okay, it's like an early hint for that. Okay, so what CLIP thinks? Some kind of heat map, of similarity heat map. So this is the first time that something from OpenAI interacted with CLIP. So they have the Colab notebook. There are 8 images in the notebook. So there is this sample set. And you have the captions there. So let me fetch. OpenAI CLIP. Here, I think it's okay. And we can also review this. So here, each backbones they have for the CLIP model, and this backbone basically extracts for you. You have the raw features. You're getting these vectors representing the raw features of it. There is the image pre-processing because the model expects a fixed size for that. So for the images, the size is 224 by 224. So it does the resizing here, performs the center crop, and normalization. Now for the text preprocessing, we have the indexes. This is the tokens, right? So if it was hello world, it gets these token IDs. This is padded to a length of 77. So all of the rest are zeros. Then it's aspect of setting up the input images and the text. So the code. So we have the description here. We have the description of the images. Now for each of the files, which is an image, what we do, we open the image, convert to RGB. This is just for all of the plots. So we have the 2x4. And what we could see basically is just a viewer, okay? Just a viewer. We have an image and the image caption on top, the image description. So basically what we do here, we normalize the images, we tokenize the input text, and then we have the inferencing, the forward pass of the model in order to get the features. So it's these parts. To get the features, you are passing it through the encoder, and the encoder, you remember, it was whichever backbone we chose, visual transformer, ResNet, etc. And now there is the aspect of calculating its cosine similarity, because you want to get a similarity score. And like we said, so if we have matrices, we want to have highest score on the diagonal, at least for the training sets, yes, for the training, for the test. And this is what we have here. So 1, 2, 3, 4, 6, 7. Okay, so we have the 8x8. The diagonal is the one with the match, meaning if I look here, it's the page of text about segmentation, and this is page of text. Here, the astronaut woman. So the portrait of an astronaut with the American flag, it's this image. Anyway, so these are the scores they received. And like we see here, those are the highest scores on the rows and the columns as well. And then we have the aspect of zero-shot image classification, okay? So here we saw we had disperse, etc. Now we want to go to zero-shot. So for the zero-shot, we took data from CFAR 100. We take the label and we add to the text saying, hey, this is a photo of something. We generate the tokens of that. We are doing the encoding for it. And we normalize. So then here we have the aspect of the probabilities themselves. And this is the result of that execution. Now, what we see here is not something which is perfect. For some of the things, it worked well, for some not. So we could look at this piece of paper, and here we can see that the maximal probability is that it's a bad, but also the score is very low. So probably we should have had some threshold, which would say, hey, I don't know what it is. I don't have the confidence. Here, on the other hand, it identifies that this is a woman. So that image of an astronaut that we had, and this is what it had in the labeling process, it was a portrait of an astronaut with the American flag. So it recognized that it's a woman. Here identifies that it's a rocket. Here there's a mistake. It thinks it's a sweet pepper. Here the horse, so gets the highest probability as a cattle. And we can also see the issue. The issue is that this sweet pepper, which is wrong, has probability of like 60%. This cattle here gets the score of 0.3. Here we can see something different, but also an issue. Two of the high scores, very high score, look almost equivalent. It says a boy and a man, but this is not someone in the middle, right? I mean, we see that this is a man. This is not some boy age of 16, but it identified here both as the same. And again, also don't forget, there are the many things that this paper brought to life. Plus, again, it was also 2021. So everything's okay, not expecting everything to be 100% perfect. Okay, and here it identifies the motorcycle in probability, which looks very close to 1. Here it looks like there is some very minor probability saying it's a bicycle. Okay. So the aspect of the zero shot that we already saw as well, but anyway, it was you're loading the clip model, you're choosing the backend, you have the model and whatever required for the pre-processing. Taking, for example, CIFAR 100 as an example, picking the test image and the build points for all of the 100 classes. So we go here through the pre-process of the image. So this is the image input. We have here the text input. We simply take the label and just attach to it a photo of A. So we don't do anything too much sophisticated here. We are running through the encoders. So we have the encoder of the image, the encoder of the text, then we are getting the raw image features. By the way, again, just remember the flow until here. The input to the encoders was the normalized, pre-processed image and text. Okay, so here we have the aspect of the normalization. And then going from cosine similarity to a softmax to extracting the top 5 probabilities. Any questions? Okay, so the zero-shot clip traveled back then the supervised ResNet 50 on ImageNet. This is something very strong statement. So anyway, so the supervised model, like we said, it was trained with full labels on each data set, training set. The clip model never saw any of these data sets. So on ImageNet, the data set that the entire computer vision community has been working on since 2012. So this was a sensational result in 2021. You take a model that never seen a labeled ImageNet image and have it match the original AlexNet era benchmark. So, and the more important finding in this aspect is the right side here. So if you looked at the ObjectNet, so it's the cousin of ImageNet. So same kind of object, but photographed in unusual orientations. So the supervised ResNet 50 went down from 76 to 41, but the zero-shot clip only dropped from 76 to 72. So same goes for other benchmarks as well. So the interpretation for that is that supervised models overfit to the photographic style of the training set. So they learn, photographs of dogs are taken usually probably in sunny outdoor, more than they learn a dog. So CLIP, given that it saw 400 million images of every conceivable style. So CLIP learns the concept itself. So when you change the photographic style, CLIP still holds up. And so this robustness story overall is arguably the deeper contribution. It reframes what good means in vision, and it's not about higher number on a single benchmark. It's also how well does the representation generalizes across the distributions. Okay. Any questions? Okay, so the implications of what did it unlock? Well, with so many things, right? So for the computer vision, you have the open vocabulary detection. It's this Graude, Dino, and others. You have the open vocabulary for segmentation, SAM clip, mask clip. You have the text conditioned image generation, stable diffusion, image retrieval, okay? Searching by text when you have billion image scale. Now, think about it. Basically, the way for this to work, because right now, so when you have your images need to go through the encoder. And then when you want to do the image retrieval, so you have the search that you're looking for. So the text goes through the same path. You're getting the embeddings, and then you do cosine similarity. By the way, equivalent mechanism to a RAG, but here on different modalities. Okay, and this is the backbone for self-supervised computer vision across the board. Now for LLMs, so it's the multimodal LLMs, GPT-4, V, Java, Gemini, Claude, Vision, etc. So the vision tokens for LLMs, basically, it's the clip encoder, the projection, the language model. So overall, it gives you like what I told before, right? It's the sort of the RAG over images. It's exactly the same trick that is used in RAG, but the embedding is just different one. Beyond that, you have image classification without any specific task labels. Okay, so many good things that by releasing it, they promote the industry. And by the way, I know that OpenAI is not open, etc. But if I was them, I would look at all the things that they did release, these research papers, all of these milestones, I would say, hey, for sure this is open, right? Because had they not shared the many things that they did share, uh, the rest of the industry wouldn't have been evolved as much as they did. But anyway, I think the major boost to the industry was simply seeing ChatGPT and all of the companies back then who were lagging, that was major motivation for them to catch up. Let's see. When it fails, so if you have something similar species, similar, different car models, but it's a car, of course, aircraft variants. So there you have different techniques. Counting objects. If you have three apples, this is an example. OCR. Okay, so the statement that it reads it poorly. And dedicated models for OCR are still state of the art. And it has some web bias, some stereotypes, right? Because this is, I don't know if to call it web, okay, so it is web bias, because also to the web, you don't necessarily get a full reflection of the reality. So anyway, it's biased toward that. Okay, so this family kept going. So there was Clip, there was from Google this line Poca, OpenClip, EverClip, etc. GPT, Dino. So that's a big contribution, like I said, to the open source ecosystem. Okay, anyway, so there are some access to the repositories, and we saw on the clip where we have the Python notebook. If anyone wants to experiment with the things we had a look at. Reading material, of course, there's always, plus we will see in the future if any other relevant model as well for us to explore. Beyond what we started also on the previous session, right? We started with Nemotron. We will also finish the review of the Nemotron paper as well. I will stop the recording. Okay, great. So I hope it was productive for you. It's a very special paper, huge impact. You need to understand it in order to understand, like, hey, why do I have sort of unsupervised learning? Okay, it's with the help of Clip. That's it. So any questions? אפשר לעבור גם לעברית. שאלות לפני שאנחנו נתנתק?
תומר, אפשר לסיים רק איתי בחירת הנושא? אם אין שאלות למישהו אחר?
כן, אוקיי, אז כולם יכולים להתנתק, בוא תשאל. כן, אז מה השאלה שלך?
כן, אז אני צריך לבחור את הנושא. מצאתי אחד, שנייה, שהוא מתעסק ב-Memory and the LLM era. אני אשלח בצ'אט. ותומר, אני עדיין לבד בפרויקט, כי אנחנו מספר זוגי, אבל עדיין לא מצאתי מישהו חסר, כאילו. כל פעם אני שואל, אבל אני לא חושב שהוא נכנס להרצאות. אז
אני
אני
גם
אעשה...
לבד בפרויקט,
הנה.
אז אם אתה
אז
רוצה שותף, אז אני...
כן, בטח, אני מחפש מישהו מתחילת הסמסטר. כל
אה,
הרצאה אני... אז
כן,
נהיה ביחד.
אין קבוצת וואטסאפ או משהו, אז לא ידעתי איך לחפש. אז בסדר,
אה,
קבענו אחי.
אתה רוצה לשמור את המספר טלפון שלי? אני אשלח
כן,
בצ'אט.
תשלח, כן, כן, תשלח.
שנייה.
אז רגע, אז מי שאמר
ליאור,
עכשיו,
ליאור, יש לך נושא?
בדקתי משהו, אבל אני לא יודע אם מישהו לקח את הנושא הזה. ראיתי שיש את הקימי 2.5, אני לא יודע אם אתה מכיר את זה, תומר, אבל לא יודע אם מישהו לקח את זה.
כן, מכיר אותו, אני לא יודע אם מישהו לקח. קימי זה כן משהו שהיה יכול להיות מאושר.
כן, וגם לקחו את דיפסיק ואת הסאם 3 ואת רוב הנפוצים.
כן,
וקווין, גם מצאתי קווין, וכבר לקחו את זה, נכון? קווין
כן,
VL.
כן, אני חושב שכן.
נימטרון 3 של NVIDIA, גם לקחו.
אוקיי. לגבי קימי, טוב, פעם הבאה אז עדיף לשאול בתחילת השיעור, כי אז אם מישהו אמר שהוא לקח, היינו יודעים. גרסה 2.5 לא יצא להם חדש יותר?
כן, ראיתי שזה יצא בינואר השנה הזאתי.
בוא נראה. לא, כן יצא 2.6.
2.6, אוקיי.
ליאור, תשלח לי בוואטסאפ, אחי.
יאללה, נשלח.
So.
אוקיי. טוב, אז בינתיים לכו על קימי. אוקיי.
אוקיי,
בסדר?
סבבה. סבבה.
סבבה.
כן.
טוב, תודה רבה, תומר.
מבחינתי אחלה.
אוקיי, עוד מישהו עם שאלות? בסדר.
תודה, תומר.
בכיף, טוב. אז אנחנו
ביי
סיימנו.
ביי.
ביי ביי.
ביי ביי.